Welcome to another episode of the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. Is Sean Groman. Sean is the co-founder and CEO of a startup called Zephyr. You can find it at zephyr.xyz and the tagline is GPS Reimagined. And I know what you're thinking. Why do we need to reimagine GPS? Is it broken? And I think Sean would argue that it's not broken, but we could be doing things better. For example, we could use software to turn every mobile phone into a base station and provide each phone with its own customized set of error corrections. There's a little bit more to it than that, but I will let Sean explain this in more detail in just a minute. First, I want to thank Planet for sponsoring this podcast episode. So if you haven't heard of Planet before, go back through the archives and look for an episode called Planet, Imaging Everything Every Day, Almost. And if you have already listened to that episode, I'm sure that you'll remember that Planet images the Earth every day to create a living data set of global change, and you don't need to learn a bunch of new tools or spend a ton of time to make use of these insights. Use Planet's satellite imagery to drive richer analysis with high spatial resolution and high frequency data, broad area coverage and automated detection feeds, integrated directly into your geospatial platform. Learn more at planet.com/GIS. Thank you very much, Planet, for making this podcast episode possible. I really appreciate your support. Hey, Sean, welcome to the podcast. It's a real pleasure to have you here. I've heard a lot about you. I've seen a lot about the new project that you're working on, and we recently had a pre-interview. So I do this with all of my guests, and it was a fascinating topic. It was a really enjoyable conversation. So I'm looking forward to this, and I want to sort of bury the lead for the listeners here. Maybe you could take over and just introduce yourself, please, to the audience. And maybe give us an idea of what you're working on today.
Well, yeah, no, thank you. Thanks for having me. I'm a big fan, so it's a real privilege to be on this side of the screen, so to speak, or the mic. But yeah, I'm really looking forward to it. Yeah, on our side, our team's been working on a new technology for improving the accuracy and resiliency of GPS, GNSS for mobile devices, but potentially other higher end receivers also.
So on your website, it says reimagining GPS, which is, awesome. Some awesome marketing has gone into that. I'm surprised you didn't say democratizing something, but you went for reimagining GPS. Why does GPS need to be reimagined?
Yeah, I think it's kind of a twofold reimagining. One is while we have a background in GNSS and mapping for quite a while, from a methodological standpoint, we kind of come from a background in physics and statistical mechanics and dealing with really large, complex data sets that are, tend to be noisy and a bit messy. And, GNS has really hard math, but typically it's not a massive data set, right? You have your satellite, your phone, and you're looking at a number of satellites and there's a discrete number of measurements that you're working with. Or you might have a base station and still like a discrete but very complex mathematical problem. And part of what we've been reimagining is saying, what if we could have way more measurements than just the measurements off your phone or the measurements from a base station? What if we sampled a huge number of phones, a huge number of GNSS receivers that were close to each other and look for the best possible combination of measurements? And so it's a bit of a methodological reimagining. What if we turn this into a big data problem where we can use a lot of the new computational AI type of tools to solve the problem, and potentially with that open doors to find new, novel, potentially better ways to get location for devices.
Okay, so let's dive into the nitty gritty of this. Another thing that says on your website is this: or what if every phone was a base station? Let's start there. What do you mean by that? And then we'll move off and talk about what this will look like in the real world.
Cool. Now, great question. Yeah, classically, when you want to do really high precision GNSS, you tap into a base station. And base stations are awesome because it's fixed infrastructure that's available around the world. There's free networks from folks like NOAA. There's also for-feed networks from great commercial providers that are out there. But in general, they all use these really precise locations and infrastructure to create an error correction. And then that error correction is sent to your rover or receiver, and it helps you get a much more precise location by canceling out the error for your signals with the really nice precise signals from the base station. And that's worked super well over the years. But those base station networks are quite expensive to run, and you got to make sure they cover everywhere. And it's quite a bit of overhead. And so the concept that we had was, we have all these phones that are out there that are increasingly getting better at what they do. And as autonomy comes along, there's a lot of other GNSS receivers that are beginning to be deployed out there. And the thought was, while those signals aren't as precise as the base station, maybe instead of getting a really precise signal where you use time to converge, maybe we could use space to converge instead, the kind of physics axiom of flipping time and space, right? So if we had a bunch of spatially diverse measurements, maybe we could get those to converge on reality, even though they're a bit noisier than what we get from the base stations. And so that was, the general idea of turning everybody's phone into a base station. Now, especially since Android has made the raw GNSS measurements available a few years back. So you can get carrier phase and pseudo range as well as the traditional code signal. You get all the same data that you get from a base station. It's just not as good. And so the idea was using some of these methodologies we had developed with other ventures and academic backgrounds and see if we could apply it to GNSS. And maybe there's something there, right? A little nugget that people haven't looked at quite yet.
Yeah, so that's really interesting. So what we're talking about here is increasing the coverage or perhaps the density of coverage of these error messages that you're getting from a GPS.
Yeah, exactly. You can kind of think of it the same way with traditional GNSS. Multi-constellation was a big win for getting better accuracy for phones, for instance, and for really any GNSS receiver, right? If you just have GPS, it works well, but it doesn't work as well if you also have Galileo, Baidu, GLONASS, NAVSEA. That you have more satellites to measure for them, better variety, better odds that you have a line of sight on that satellite, and it just makes your result better. And so we've basically flipped that terrestrially. In addition to having multiple constellations, what if you had multiple receivers looking for the best possible measurements? So while your phone, you might be next to a big building or just stepped inside, and so you have an occluded line of sight or partial. You can only see a few satellites, but there could be somebody across the street or in the park that has full line of sight on a bunch of satellites. So if we can share these measurements across devices in a secure and anonymous way, then there's a potential we can find a better combination of measurements to do a nice error correction for everybody in that geography.
Are we talking about building a mesh network then between phones, between devices?
Yeah, it's a mesh in a sense, and there's a couple of ways that we could go about it. Since we're an early stage company, really just have access to the APIs that the operating systems make available, and so wonderfully, Google's made these measurements available through Android, which is a real godsend to being able to do these kind of innovations. But it pretty much means that to create a mesh, we need to send those measurements up to a server to solve that optimization problem, to create that loss function, and then generate an error correction. If we had access at a lower level, we could potentially do a mesh from device to device, a proper peer-to-peer mesh. But right now, the access that we have, it's to those measurements through the API. So a server-based solution works best for that. Although it takes, you have to be a bit more careful with your privacy considerations and making sure that it's really secure and you're doing that in a thoughtful way. But it works quite well for the initial scenario.
I noticed you mentioned one of the phone manufacturers there, or not phone manufacturers, but one of the developers of the Android platform. So Android phones. What about the other one? What about the elephant in the room? What about Apple?
Yeah, I mean, Apple today, while they do have that data available within the phone and the operating system, that data is not made available to developers. And that's, kind of, Apple's philosophy. It's very kind of privacy first, and they want to make sure that there's a good reason for exposing data. And, so we're hopeful in the future that, that Apple may see utility in making that data available. And that's, a potential opportunity going forward, but it's not that way today. I mean, Google does provide it so we can prove out the efficacy of the approach and that it's viable. And so that's really where our focus has been in the short term.
Does this mean then that the network that we're talking about between these phones, mobile devices, are we going to have broadcasters and receivers in that network? Could Apple phones still participate in the network, get the benefits of this simply by consuming the data as opposed to broadcasting these error corrections?
Unfortunately, no, not at least the way that it's structured today. In order for the error correction to work on the phone, you need to have an understanding of the ambiguities that it's generating. So each error correction is specific to the phone that it's sent to. While we're only sending the error correction, we're not sending the location of the phone, and we don't keep any of the measurements to ensure privacy. That error correction is specific to the device. And so if you don't have the measurements from the device, it's difficult to give it the correct error correction. So unfortunately, it needs to be a kind of a two-sided equation for participation in order to get the benefit of it.
I appreciate the clarification, and please don't take any of this as a critique. I'm just trying to understand the concept. So if I tried to summarize this now, I'd say something like your realization is that what if we had a higher density of data points on the ground, and what if we shared that information between devices on the ground and used that to create these more accurate locations? And what if we did the processing ourselves? So it sounds like I'm a phone, I'm an Android device participating in this network. I send my raw GPS data to your server. You create an error correction and send that back to me, and I can use that to update or to correct my location.
Yeah, no, that's spot on. In many ways, it's much the same way the base station network works today, except for instead of having a single base station that gets a really precise signal to create that error correction, we're turning it into a combinatorial problem of that we have a bunch of receivers out there that are getting measurements. Some of those measurements are good, some of them are mediocre, and some of them can be quite bad. So we pull all of those measurements into this optimizer, and it runs an ensemble to look for the best combination of measurements that will create the best possible error correction, and then shares that error correction customized to each phone, but generalized to that kind of micro geography.
And how many phones do you need? Like, how many error corrections or these sort of mobile base stations do you need within a geography of, let's say, 10, 20 square kilometers to see a difference, to see an increase in accuracy?
Yeah, that's a great question. Even with one receiver, you can still improve the location with a basic code minus carrier calculation and some other really careful and thoughtful considerations of the parameters when you're solving the problem. But ideally, we'd like to have four devices. And the field test that we published with announcing the company was using four Google Pixel 4 phones. And with that, we're able to get in an open sky scenario an average error of 55 centimeters. So even with as few as four devices and three devices, you can get a decent result also. After about 10 devices or so, you begin to get diminishing returns, and that the additional data doesn't give you a meaningful increase in accuracy, but it does give you more computational load. So there's kind of a really nice optimal window between about 4 and 10 devices.
So, from previous conversations with people working on solving similar problems, a lot of them have mentioned that solving this GNSS problem is really computationally heavy. Like it requires a lot of compute on the device anyway. Now, I understand that you're doing some of this server side. What about the communication burden? I mean, if I have to, I don't know, receive a new data packet from you or reach out, do I have to send a push notification to the server every time my GPS updates?
Yeah, another really great question. And that's one of the things that was a really nice upside we found when we were doing the simulation and testing and then the deployment is that the error correction persists for as long as you have lock on the satellites. So we don't need to send a new correction every time you get a new GPS ping, because that definitely would kill the battery if we were having to create the error correction and send it down every time the GPS updated. But fortunately, that's not the case. You send down the error correction when you first jump onto the network, and then that error correction persists until you lose lock on the satellite. Which typically can be several minutes. Before you get, you go into a tunnel or you go inside or you turn off the app, and then you lose that lock. And then at which point we need to send a new error correction, and bring you back onto the network. The good news is since we're getting measurements from so many devices, is the network's always warm. You're not having to do a cold start and resolve your integer ambiguity space to find that location solution. There's a whole bunch of devices that are already locked on and have that solution nearby. And so you can kind of think of it as a cheat code. To make a bad metaphor, you can get the cheat code to solve your ambiguity space and get locked in very, very quickly. So we did a ton of simulation modeling with SRI over in Palo Alto, which has a wonderful PNT group in their applied physics lab, a bunch of really smart PhDs that helped us, game through all this, benchmark it, simulate it, and do all those kind of good things. And that was one of the cool things we found was that with this warm network, recovery from outages and drops was way faster than in a standalone scenario, which was another cool thing that got us excited about the approach, that it's more than just accuracy. You also get much better resiliency and robustness in your network and the ability to recover from outages and losing line of sight and things along those lines.
So, I mean, it sounds amazing, right? It sounds fantastic. How are you going to build the network?
Yeah, it's another wonderful question. And here we're really, piggybacking or standing on giants that, for us, the real target market initially are these location-based applications that already have a huge number of users. The rideshare companies of the world, the fitness trackers, the data collection networks that are, going out and like OpenStreetMap and, looking to collect new data to create open data products, or, want to map fire hydrants for the city, et cetera. That there's already these, wonderful apps that are out there that use GPS and GNSS as is, but the location isn't as good as it could be, right? So the rideshare shows up on the wrong block or the wrong side of the street and it has to circle around. Or your Strava.com is king of the mountain. It might be a little dubious because you had a GPS error that made it fast, or the tracking the amount of distance that you ran, isn't accurate because you ran the same route today as you did yesterday, and it's half a kilometer different. All these things are, kind of come down to the error and noise within the GPS signal. So if we can improve that, 3, 4, 5x, our feeling is that's going to make for much better app experiences and much more reason to enable GPS on your phone and to utilize that. And hopefully create some new use cases, right? There's some things you just can't do because GPS isn't accurate enough for it.
I really want to talk about some of these use cases later on. But my question to you now is, so that this sounds like a great approach, right? And you're obviously a brilliant entrepreneur. You've planned this out, and you can see a pathway forward for this. But do these people, these networks that you're hoping to, quote unquote, take advantage of, do they already know that they need this? Like, are they? Because it seems to me that ride sharing isn't broken; it works. A lot of people use it on a daily basis. A food delivery works as it is today. Do they already understand that today the benefits of increasing the accuracy of their location information by 2-3 meters?
Yeah, I think so, at least based on our conversations with a lot of these folks. And we kind of came to this idea from our own frustrations with the accuracy of GPS with our previous startup. And then that ended up at Snapchat. And there's a lot of things we wanted to do within augmented reality, and the accuracy of GPS prevented us from doing that. So a bit of this was, solving our own problem. And then, once we kind of went down this journey, we started talking to other friends in the mapping industry, talking to friends at rideshare companies and fitness trackers and things along those lines. And we heard the same story kind of repeatedly of like, GPS is wonderful, but there are challenges that the accuracy, especially in dense urban areas, causes a lot of headaches. We've kind of learned to live with it, and we've put a lot of crutches and band-aids around it to make it work. But at the end of the day, we could be much better if we had better data, better raw signal against it. And, a lot of the folks we talked to, that headache is lost money. And that, one of the rideshare companies we were talking to was saying that for every second that they can save for the time it takes to pick up a rideshare or drop off a food delivery, they make another $1.5 million per year, just because they're doing so many deliveries, so many, pickups and drop-offs that, every time that you do that lap around the block to pick up the person because you missed them, or you're on the phone with the rideshare person saying, "Hey, I'm the tall guy in the blue hat and the gray shirt on the corner," and you're trying to find each other, right? That's another 2 or 3 minutes that they're not doing the next pickup, right? And those inefficiencies add up to millions of dollars over time. And that amount of noise in the system is just perturbated in a lot of different industries. And sometimes it's money, sometimes it's customer complaints, sometimes it's inaccuracies, and all these things can be better. So I think there's a lot of interest that we've found inbound on it that we think just opens up some interesting doors to explore.
Okay, so it sounds like you've got this brilliant idea that works, at least in testing and the simulation that you've done. You know that you can take advantage of these networks, these huge sort of networks. We talked about ride sharing, food delivery, these location-based networks that are out there in the world. And it sounds like the people that are running these networks understand the value and can see like a business case for implementing this. How do they want it implemented? Is this going to be another standalone app on my device, or is this going to be an SDK, or maybe something different, or a piece of hardware?
Yeah, no, and that's one of the things that also excited us about the approach is that traditionally in GNSS, when you have a new technology or a new technique, you need to get it onto the chipset and get it onto the hardware, through an OEM relationship or something like that. So, it's like when dual band GPS came along, you had to get a dual band GNSS chip into the phone, and then that gets deployed out, and it takes a while for people to adopt and get the new technology. And even if it's firmware, and you have a new calculation that you want to put on the chipset, you still have to go work with the vendor to get your firmware deployed onto that hardware. But the cool thing with this is that it's purely software based, and that it to your point, it's just an SDK, right? So if you're a rideshare company or a fitness tracking company or whatever the case may be, and you want more accurate location for your users, it's just a matter of putting that SDK code into the app, and then we start improving the accuracy for all those users.
So I realized earlier on in the conversation, you said something like half meter error, that in testing, you could bring the error down to half a meter as opposed to, I'm not exactly sure what it was, maybe 3, 4, 5 meters. That seems realistic when we're talking about using a mobile device. Is there a world where this error is much, like, significantly smaller than this half meter?
Yeah, there's a mathematical floor, at least with like a floating position within it. We roughly, within our mathematical calculations, 10 centimeters is kind of like the best possible outcome. If you add in some fixed positioning, maybe it could get better. But the reality of the antenna within the mobile devices not being external, it being packed inside your phone with a lot of other electronics in a metal case, just introduces a lot of noise. So like our test, we were at 55 centimeters, but that was just using the GPS constellation and just using the L1 band. So we still have more constellations we can add, and we can add in the niceness of the dual band to do atmospheric corrections. So we feel pretty confident we can get below 50 centimeters. Where between 50 and 10 we might be able to end up is to be determined. We're hopeful to get it, to continue to push it down. In simulation, we're able to get down to 30 centimeters, but the real world's always noisier than simulation and a bit messier. So I think the reality is somewhere below 50, but probably not massively below 50, unless we come up with another great innovative lever to pull. But with our current set of levers, that kind of looks to be where our potential is at.
But when you're talking about these levers that you can pull on, so you mentioned multi-constellation there, is there an opportunity to take advantage of the IMU, perhaps use some dead reckoning in there? Is there any other sort of sensor fusion techniques that you can see that are going to be part of this future?
Yeah, most definitely. That's big next on our roadmap. Once we kind of get everything we can out of the GNSS sensor, is then to look at the next set of sensors that we can work with. And IMU is top of the list there. Especially looking at pose prediction is one thing we're particularly interested in. Our background coming into this was visual positioning systems, and so we spent a lot of time thinking about how positioning works within a 3D space. I think it was your guest Sandy that talked about there's like kind of two aspects to positioning. One is your XY location, and the other one is what are you looking at. And visual positioning is brilliant for what you're looking at. And so we learned quite a bit in our time with Snapchat and in our own time working with customers with Pixelate, our previous venture. So we'd like to bring a lot of what we learned there to the sensor fusion piece of this. How well can we do pose prediction? How well can we potentially do 3D body tracking? How can we potentially tap into multiple IMUs when people are wearing them? Because I think we think about the IMU on our phone being the most obvious one, but most AirPods and earbuds and so forth often have an IMU in them. Your smartwatch has an IMU often in it. Smart eyewear has IMUs in them, fitness trackers and so forth. So there's lots of potential data that we can be collecting and using to be very, very much smarter about this overall positioning question, where it's much more than just our XYZ. What's our kind of 6 degree of freedom look of positioning going forward.
You mentioned your background in visual positioning there, and this has been, in my mind anyway, a relatively hot topic recently. Do you see these two techniques, what you're building and visual positioning, as being adversarial or complementary?
I think they're inevitably complementary in that a big part of making VPS work is GPS. The better GPS precursor you have, the better your VPS will run, because you're constraining your search space. Again, depending on the type of VPS that you're running, having the GPS precursor being more accurate is a huge help. And it was a big limiter for us in our previous VPS work. So they do go hand in hand. I think one of the challenges that we saw at the time that we worked on VPS, not only at Snapchat but working with some of the other big players before we ended up at Snapchat, is just how incredibly expensive VPS is from two different perspectives. One is data collection. If you're Google or an Apple and you already have a Street View fleet that's out there, and in Google's case, a fleet of airplanes to do aerial imagery collection, or big budgets that Apple has to collect things, those data inputs are there, but it's still, it's $1 billion operation to maintain and collect all this data on a regular basis. So for most other companies in the world, replicating that fleet of Street View and aerial assets is really intimidating for the reasons that it costs billions of dollars. And then you have to process the data, creating a 3D reconstruction and computationally to create a feature database to power a visual positioning system is computationally very expensive as well. There's several startups that, found that their AWS bills were quickly outstripping even like their labor costs trying to solve this visual positioning problem. And so, those two sides of the coin are incredibly expensive. And so, maintaining a global visual positioning system database and having to build the world in 3D and update it on a regular basis might not be the best way to go forward for, an augmented and autonomous future. If we can do more of these things with sensors where we don't have to map it out ahead of time, there certainly are, lots of use cases where the VPS fits nicely. But I think as a global solution, it's going to be challenging from an economic perspective. At least if we think about these things having lots of participants and lots of developers in them. And if we can do more on the phone, do more with post prediction and 3D body tracking and absolute positioning, and just using that with the sensors on the phone or the sensors on the autonomous vehicle or robot or drone, whatever the case may be, that just drives down the cost. And then it increases the opportunity for more people to participate, more people to innovate, and for all of this kind of future to happen more quickly, I think.
So just piggybacking on that, in a previous conversation, you talked about this idea that it's cheaper to solve these problems in positioning space than it is in computer vision space. And you made a great case for that, pointing out that, wow, building these baseline data sets is really expensive, let alone maintaining them. Is that statement also true when we think about the act of somebody taking up their phone, in the case of Google and Google Maps, for example, and waving it around like this? Is that more computationally heavy than it is to do that kind of piece of the visual positioning, as opposed to solving it in GNSS world?
Yeah, I mean, yes. Generally, the way that manifests itself is in battery drain. That having to hold the phone up and run the camera as well as doing the computation. And it depends. Like Apple tends to do that on the phone for privacy reasons. Google tends to do that server side for their visual positioning. So Apple, the feature database is loaded locally on the phone. And then when you move to the next place, it removes that feature database and replaces it with a new one, kind of the same way we swap out tiles. Google, you hit the server and the server does the visual computation. There's, pros and cons and trade-offs. They both work quite well. And it just kind of depends on what you're optimizing around. But in either scenario, either you're doing a lot of computation or a lot of battery drain. And that's, where these things get difficult. And then there's also the modality problem. It was funny. Somebody had done a post on LinkedIn asking about a visual positioning solution for an airport and saying, would you use this? And the comment sections were fascinating of people that had used visual positioning in airports and saying that one of the biggest problems is feeling like you're like an Instagram influencer because you're walking around with your phone up like you're collecting a video because you need that to be able to orient to look through the camera, and that just being awkward and feeling a little weird for people. Whereas like having the phone down and looking at a map to navigate, we're all used to doing and feels less weird from a social engagement and interaction standpoint. And we ran into this a lot, also both at Snapchat and with the previous company of thinking about ways to make that less weird without needing glasses. So actually, auditory is a really interesting one, right? If you have earbuds in and you're navigating through audio cues, and then you still might be orienting from an AR perspective or from a positioning perspective. But for instance, let's say we wanted to have with 50 centimeter accuracy, potentially play a game of tag, or as you get below 50 centimeters. But you wouldn't want to be holding up your phone while you play the game of tag. But if you had AirPods in, and then the tag is triggered, and you get an auditory track for that, and it's also being tracked on the phone, that becomes an interesting way to kind of get around some of these modality problems. All these are kind of like pre-AR glasses problems. Once we get AR glasses that are functional and work, a lot of these problems go away. But the positioning stuff is all important. Just the modality part becomes easier.
Yeah. So again, that makes a lot of sense, and it's interesting the cultural aspect to this. People don't want to walk around with their phone up. So, like you were saying in acting like an Instagram influencer. They don't like that. They're used to having it down. It seems trivial, but if that's the thing stopping you, going to market, as it were, getting people to use your product, it's worth recognizing that. I think maybe as technologists, a lot of times it's easy to think, oh, well, they could just do it, right? Come on, just do the thing and let's move on. This is an amazing app. This is amazing technology. Just use it anyway. I like the fact that you recognize that. I want to head off into this sort of autonomous world in AI, VR future that we've been promised. And so my question around this is, knowing your absolute position in a global context, is that enough to fulfill this promise? Or do we need something else?
No, unfortunately, I don't think it is quite enough. Going back to a bit of what we were talking about, that it's important to not only know your XYZ, but also, that 6 degree of freedom, or at least 3 degrees of freedom of what are you looking at, how are you oriented, what is your body or vehicle's positioning relative to other things in the network. All these additional measurements, we take for granted as humans when we move through space, because we see what's in front of us, we interact with things, we have our own depth perception, that we need these kind of things also within an autonomous or augmented future as well. And I think, that's going back to the, kind of the sensor fusion IMU discussion, that we're going to need to figure out how to bring all these technologies together in a way that's scalable and technologically feasible, but also works economically. There's a lot of challenges, I think, especially if we go back to the positioning space, that RTK is wonderful. We get super precise accuracy from it, but the cost to connect to a correction service and get that accuracy at the geographic coverage that these applications need is quite expensive, right? And so, while it's fine for like a test bed in San Francisco, let's say for autonomous vehicles, you're going to put every sensor in. Price is not so much an option. So you just want to make it safe as you can. But when we start talking about, thousands, tens of thousands, millions of autonomous things, I think we're going to need a much more economically viable way to roll these things out.
I don't think we've mentioned this, but I think you're hinting at it here now, is that this is not exclusive to phones. So this technology that you're building, this idea that you've got, it doesn't sound like it is just for phones. It sounds like it's for devices that have the ability to communicate across a network, and devices that have compute on board, and devices that have a GNSS chip.
Yeah, exactly. I mean, phones was a really good place for us to start, because one, it's probably the hardest problem. If you can get a solution to work on phones with a crummy antenna, then you're going to be in really good shape to do it where you have a dedicated antenna and a higher end receiver. The other nice thing about it is phones are cheap and they're ubiquitous. And so as a small startup, bootstrapping along, buying a whole bunch of used Pixel 4s on back market is, $100 a pop, right? And you can get a bunch of receivers and test things out really easily. And again, props to Google for making the GNSS style receiver data available on the phone. And then also the Kaggle challenge, which gives you a bunch of data. They have a decimeter challenge on Kaggle that gives you a bunch of test data to work with, which also is super helpful. And then a whole bunch of other people that have entered the contest and seeing how they've tried to solve the problem. So all those things made, phones very appealing. And then, the thought was, if we can get it to work on phones, then, we can probably get it to work on higher end receivers. I think, the thing that interested us there was, in many ways, we're creating an error correction organically from the devices that are already there. And a lot of times, for a lot of scenarios, oftentimes a correction service base station infrastructure is not available, or it's cost prohibitive, right? Most correction services commercially are, tens of dollars to hundreds of dollars per month per device. And while that's great for a lot of use cases and it makes sense, I think there's a lot of new emerging use cases where those economics might not make sense, right? Where if you're looking again at massive fleets of autonomous things, having that kind of overhead to provide a correction service for them can make a lot of use cases not economically feasible. So that's one thing we're hoping to move into. And we're doing some field testing now of taking some higher end GNSS receivers and testing with those to see how accurate of an error correction we can create just with the receivers themselves and not using a base station network, and see how viable that could be as far as what level of accuracy. And then we're hopeful that, if you can really drive down the economics of there, maybe we can open up entirely new use cases for using RTK in ways that are much more, viable, because you drive the cost down enough to make that level of precision available. You can do new and interesting things. And I think especially as a company that's positioning itself to enable developers and developers at companies to do new things, that's exciting because we've already seen it with the brief time that we've been around, the inbound from developers of how they've thought about using this new capability is really exciting and inspiring. I mean, they're so much smarter than we are about how they might use this for their particular use case and their particular niche that they've been thinking about. That's fun. And so we think if we can open up more opportunities, open up more markets, we'll see more creativity and innovation and people doing cool things.
Is this somehow going to solve part of the solution around people spoofing their location and provide that maybe a little bit of extra security around like proof of location, proof that this device was there because it's participating in the network?
Yeah, no, it's funny. I literally had downloaded a spoofer earlier this week, and we talked about this a little bit on the pre-interview. So, and basically, I was curious what would happen if I ran a spoofer through our own platform and what it would look like. Because the spoofers have gotten quite sophisticated, and I always wonder like how much of it is catering to like the Pokemon Go community of helping you go get that Pokemon, even though you're geographically can't be wherever that Pokemon is. But it's really amazing how sophisticated they are. Like you can go in and say, not only I want to set my location is instead of being here in Boulder, Colorado, I'm in Bangalore, India, right? And actually, big tech companies have got really good at finding that kind of spoofing. Like we had this problem at Snapchat where people would fake spoof stories to the Snap Map as spam so that they could get traffic. And so, detecting that teleportation that all of a sudden you went from Boulder to Bangalore, people have gotten pretty good. At least, big tech companies have been good at finding that. But then the spoofers come back in turn and say, I know, now we're going to randomly change your location in a place within a constrained area so that you can stay in that location and create a history of locations there. And then, people started to test to find the location's random. It's not following like a set path. And so then the spoofers started making it so that you could set a route and say, I'm going to go down Main Street, take a left on First Street, and go to Squirrel Street, which again makes it tougher. But the cool thing is when we ran that spoofer and we put it through our own system, of course, the spoofers, at least the more basic consumer ones, they don't have satellite measurements, right? There's no code signal, there's no pseudo range, there's no carrier phase, there's no like raw satellite measurements that a spoofer generates. There are, if you go like to the nation state level, like military applications, there are spoofers that simulate that data. But we think even in that case, right, when you're running this optimizer, you get really good at finding the good signals and the bad signals. And a simulated signal, at least we think, would stick out as a bit of a sore thumb compared to things that were naturally occurring. But that's TBD. But from the basic standpoint, from location-based applications and the way at least I've seen them spoofed in my own experience, that we do quite well at that just because the spoofers aren't creating actual satellite measurements and we depend on satellite measurements to solve it. So when you come in and you don't have satellite measurements or you're faking your movement, you're missing that. So it does work quite nicely for finding spoof things, at least in our testing so far.
That is really interesting. I had no clue that it was that sophisticated that you could, start creating almost like a bot and get it to walk around a street at a certain path to try and simulate being a human and make it look normal and not stand out in the signal. That's fascinating.
Yeah, people will jump through amazing hoops to get Pokemon. It's kind of wild.
I'd like to try and wrap this conversation up now, and I want to do that by looking at this as a business idea. So you've mentioned pieces of it, throughout the conversation. Why it's a good idea, why you think you can solve the problem, the proof that you've collected on the way, the conversations that you've had with people that are potentially going to be interested in either investing in the company or buying the product or the different use cases they have for it. Could you package this up for us and like tell us what the components of a good business idea look like for you? I realize it's a broad question, but I think it would be really interesting to hear it from someone like you that's had successful exits in the past, that has built successful companies, and has tried this a few times.
Yeah, no, it's another great question. I think the way we think about it is really value-based pricing, and that you want an unequal exchange of value with the companies, the customers that you have. And by unequal, I mean you want to be giving way more value than the compensation that you're taking back. And so, for instance, like with location-based applications, we think a lot about what's the ARPU or the average revenue per user within these big rideshare fitness tracking data applications that use GPS on your phone. And then how can we add more value to that. How many millions of dollars can you save if you're a rideshare company by having fewer of those trips around the block? Or how much value can you add by giving more accurate statistics to your users? How many more users could you gain from that? Or could you actually do accurate race tracking? But a lot of folks that either do automotive or bike races or foot races, and have asked, could we just use GPS on devices instead of having to use like RFID and these expensive timing systems that they use? But across all those, right, you want to open up new opportunities that's going to create a lot of economic value and additional revenue. And then basically, you want to ask for a fraction of that in recompense. So we think of business models on the order of, a penny or pennies per user per month, right? To give you all that additional extra spatial positioning information that, is easy for you to monetize. So you're pushing up that ARPU from like, $5 to $7 or, $5 to $10. And then, asking for, a few pennies of that ARPU back again. Those are the kind of business models that we find are those really wonderful win-wins. Because these platforms have millions of users, and so you can have a great business on pennies per users per month. Obviously, in enterprise applications, there aren't as many users, so it's not necessarily going to be pennies per user per month. But again, you're looking at a fraction of the cost compared to tens or hundreds of dollars, per device or per user per month. And a lot of that comes into really being thoughtful about your cost of goods sold and how efficiently you can run your infrastructure and provide that value. And if you can find a way to do that really cheaply so that you provide some new economic opportunity so that you're saving your customers money while still generating, lots of revenue on your end because your costs are much lower and you can be more efficient. So those are kind of the classic, business model scenarios that you're looking for, where you can be really competitive on price and deliver equal or better value than what's out there on the market currently. And we find those kind of things tend to work out well because customers are happy. You're happy because you're generating the revenue you need to grow the business, and you're creating new opportunities that weren't there before.
How do you avoid that scenario not turning into a race to the bottom?
Again, it's kind of focusing on the cost side, right? That in order for that not to be a race to the bottom is you need to come up with a way to radically change that cost structure. And that's where we're particularly excited, whether it's the mobile market or the mobile phone market or the emerging autonomous market, that you can really change that cost infrastructure, right? Because if you're building these error corrections organically using the devices that are already out there, that gets rid of a lot of fixed cost that you need to put into place. And so that kind of enables that disruption to push on price because you've removed a lot of cost from your equation in kind of a classic macroeconomic or microeconomic sense. In that way, you're just changing the definition of what the bottom is, right? If you have a huge amount of infrastructure costs, it's shallow and the bottom shows up really quickly. But if you can fundamentally change that cost structure, you create a much deeper pool, right? And so, it's kind of reframing that from a competition standpoint.
Well, I think this is probably a good time to say thank you very much. I really appreciate your time. I really enjoyed the pre-interview talk that we had, and this one here has lived up to my expectations as well. It's been great talking with you. I've learned a ton. I really hope the listeners have learned a lot as well. Where can they go? We haven't mentioned this actually. Where can they go if they want to reach out to you, if they want to carry on this conversation, if they've got questions for you, if they want to read more, learn more about what it is that you're building?
Yeah, definitely. Zephyr.xyz is our website. We're so happy that domain came along. It's so great for spatial positioning things. And it gives you a bunch of new domains to jump into. So yeah, the Zephyr and XYZ is the website. And you can reach out there or at Sean Gorman on Twitter or same on LinkedIn. And always happy to talk to people and discuss use cases and take feedback and so forth. And thank you for the opportunity. I'm a big fan of this show, so it's really cool to get a chance to actually be on it.
Well, thank you very much for your time, and thanks for that compliment. Really appreciate it. Cheers.
Thanks.
Thanks again to Planet for making this podcast episode possible. Planet images the Earth every day to create a living data set of global change, and you don't need to learn a ton of new tools or spend loads of time to make use of the latest insights. Use Planet satellite imagery to drive richer analysis with high spatial resolution and high frequency data. broad area coverage, and automated detection feeds integrated directly into your geospatial platform. You can learn more at planet.com/GIS. I really hope you enjoyed that episode with Sean. I'll put links to his startup, Zephyr.xyz, in the show notes so you can check it out there. I will also include links to other relevant podcast episodes that I think that you will find interesting. So thank you very much for listening in all the way to the end. It's much appreciated. I'll be back again soon. I hope that you'll join me then. Bye.